Hi, welcome to the ICLR Friday Forum for May 10th, 2024. I'm your host, Dr. Keith Porter, ICLR's Chief Engineer. I'm speaking to you from London, Ontario. This is webinar 216 in a series hosted by ICLR, the Institute for Catastrophic Loss Reduction, Canada's leading source for disaster resilience knowledge. Each month, we present recently completed research related to ICLR's mission to make Canada more resilient to natural disasters. Last month, you'll recall that Dr. Simon Eng told us about groundbreaking new hail science by the Northern Hail Project in Alberta. Next month, on June 14th, 2024, we turn to construction practices when Patrick Foisey of Hague Engineering will talk about good and bad roofing and siding. Today, we're talking about earthquakes and how they can more strongly shake one house than another in the same neighborhood or cause the ground to liquefy here, but not there. Our speaker is Professor Sherry Molnar from Western University here in London. She's been leading an almost decade-long project to map earthquake-related soil conditions in Metro Vancouver. These soil conditions can vary over very short spaces, affecting shaking, landsliding, and liquefaction hazards that different buildings in the same neighborhood would face. Sherry's research products will help us manage earthquake risk on a neighborhood by neighborhood basis. A bit about her qualifications. Professor Molnar is an earthquake engineer and an earthquake seismologist. That means that she studies how seismic waves change and amplify as they travel from an earthquake rupture to the undersides of buildings and how they trigger landslides and liquefaction. She's Canada's foremost expert on measuring and mapping these conditions, judging by the number of scholarly publications that cite her. ICLR is fortunate to be able to work with her. Now, before our speaker begins, here's our agenda. Our webinar will last 90 minutes. Our speaker will present for about half that time. Then I will moderate Q&A for the rest of the time. Please feel free to chat your questions into the Q&A box. I'll try to pose your questions in the order they appear in the Q&A box. If we have a lot of questions, I may only pose your first question, then I'll move on to others, then circle back to your additional questions. Our webinar is recorded, and ICLR will post our speakers' slides and a link to the video on Monday or so. So if you have colleagues who couldn't attend, let them know. Thanks again, Sherry, for speaking today, and take it away.
Great. Thank you so much, Keith. And I appreciate the opportunity to present this to you today. It's not often that I get a full 90 minutes to talk about our project. And so I'm going to monopolize that time and try and explain our whole project to you in the time allotted. I am here on behalf of a large group, a team that has worked on this project currently for 7 years and eventually ending up at 9 years. So I need to start with explaining some seismic hazards to you. I assume you understand that the most primary seismic hazard, or when I say the word seismic hazard, I know about and think about ground shaking or ground motions, feeling those seismic energy reaching the surface, causing vibrations, and for me to feel that shaking. There are also secondary seismic hazards like ground deformation or tsunami waves that might occur after or because that earthquake had occurred. In terms of microzonation mapping, we primarily map or work on the seismic hazards that have to do with shaking, liquefaction, and landslides, whether or not liquefaction or landslides will be induced or triggered by the seismic energy or those seismic waves. In terms of ground motions or shaking as a seismic hazard, a most classic example that I can give to you is from the 1985 magnitude 8 Mayachin earthquake that was 400 kilometers away from Mexico City. And so for that distance, the shaking shouldn't have been too strong. And you can see the time history ground motion recording in the top left that was on rock outside of Mexico City. But inside Mexico City, where the city is built on a dried lake bed and very soft lake sediments, the shaking was 5 times stronger. And what's cool about that clay is that it has a particular thickness and velocity that filters or amplifies that shaking in a particular period band. In this case, it was 2 seconds. Or in 10 seconds, you would have felt like you were going up and down 5 times. and that's relatively long period shaking. What that means is that buildings that respond or vibrate at that same period or same frequency have a problem dealing with that amplified energy coming into the foundation and up and propagating into the building. So the cool thing that we try to do is not to do that in future, not to put buildings where they will be coupled well with what the resonance frequency of the ground is like. I will say, though, that engineers can design and make sure that the building wouldn't collapse, but only if they know what the ground conditions are like and what that period of frequency of vibration might be. For liquefaction, I want you to understand what that means when I say that word. And for us, it means that sand will bubble up onto the surface because of the shaking that's happening in the subsurface. Or the sand was sitting there just quietly while an earthquake energy or seismic waves started to propagate, started to shake it, and the water that's between these grains of most likely sands in the subsurface exceeds some pressures and start to try to filter up to the surface. So the water and the sand bubbles up, and we call this sand boiling. The fact that you've got material coming from below and reaching to the surface leaves potentially spaces or cavities in the subsurface, and so that can lead to cracking or settlement or subsidence. I want to give you an example for British Columbia where we're aware that this has occurred in the past. We do see columns of sand percolating up through other layers, and the timing of that seems to correlate with past earthquakes. So we're pretty convinced that liquefaction has been triggered in the past in the Fraser River Delta. The manifestations are the kind of impacts you would see from liquefaction, as we talked about, sand getting up onto the surface, leading to settlements, and therefore anything sitting on the surface might settle or tilt or subside in odd ways. As well as not only is the sand in the subsurface, but pipes or sewers will also percolate up to the surface because of that water pressure bringing that up during the seismic shaking. In terms of landslides, we are talking about materials that move down slopes. That material could be a rock, could be earth, could be mud, could be debris. And because of the type of that material, the way it falls or topples or slides or spreads depends on what kind of material it's made of. So when I use the word landslide, or the fact that we've made landslide maps, it includes all these types of slope failures or movement of material down a slope under the force of gravity. Again, some local pictures to try to convey to you that in the past we have had landslides that have been triggered by earthquakes on Vancouver Island, as well as in south of Vancouver in the Puget Sound or Pacific Northwest. As it's understood that the material is coming down from high elevations to lower elevations, you're going to have that material ending up in waterways or on the roadways, causing disruptions to utilities or in the environment. So with that background on seismic hazards, I'd like to introduce you to the fact that we've tried to map these seismic hazards regionally or specific to Metro Vancouver. So our project began in 2017, and over time, we've incrementally moved eastward and have added communities. As of this summer, we're going to start to release maps for Western Metro Vancouver, shown on the map area, for this summer in 2024. And we'll continue to do the mapping into 2026 to release the maps for Eastern Metro Vancouver later in 2026. So we're generating a whole bunch of maps, a suite of maps that are region-specific seismic hazard maps. That means the maps include how the variation in these earthquake hazards will vary across this region due to the local subsurface site conditions. So this research is accomplished by my team and myself at the University of Western Ontario in collaboration with ICLR. And it's a $4.4 million project supported by the British Columbia Ministry of Emergency Management and Climate Readiness. Specifically, our project is tasked with or working towards making regional seismic microzonation maps that include what will happen to the earthquake shaking as it propagates up through a soil column, one-dimensional or vertically towards surface. Another problem for Metro Vancouver, though, is that it sits within the late Cretaceous sedimentary Georgia Basin, and this also has lower velocities, softer material rock that can amplify ground motions, increase the ground motions, but also kind of trap them within that three-dimensional structure of the basin. And uniquely, our project is also trying to include the three-dimensional basin shaking effects in our mapping. We also work towards generating maps of landslide hazard and liquefaction hazard potential. So that's why we make so many maps and we look at these specific types of seismic hazards. Why are we doing this project for Metro Vancouver? I assume you're aware that the highest seismic risk in Canada is for Metro Vancouver. So we should have made the maps by now. The problem is it's a little complicated for Metro Vancouver. You're in a very active tectonic region where different types of earthquakes can occur, and the variability in the subsurface ground conditions is wildly different than other places in Canada. So it's a kind of technical challenge that we've had to overcome in the project. At the same time, it's not to say successes haven't happened in the past. There are level 1 or level 2 seismic microzonation maps or earlier versions of these maps available for particular municipalities or communities. What our project is kind of focused on is making sure that it's equitable, systematic, and comprehensive for all of Metro Vancouver, and that we're achieving very high quality, high level seismic microzonation maps for the entire region. I want to explain a little more about the complicated seismic hazard in Metro Vancouver. So we are in the Cascadia subduction zone, the northern extent of it. It extends all the way south to Northern California. This is a 1,000-kilometer fault zone and a couple 100 kilometers wide. So if the whole thing ruptured on that interface fault between the subducting Juan de Fuca plate and the overriding North America plate, we would have up to a magnitude 9 earthquake. The fact that there's this compressive regime from these two plates coming together also causes earthquakes to occur in the subducting Juan de Fuca plate at about 50 kilometers depth beneath Vancouver, but also in the overriding North America plate at maybe 5 and also around 20 kilometers depth. So that's a lot, but that also leads to why we have relatively high regional seismic shaking, because we know where these earthquakes happen and we know generally how often they're happening. So we can predict on an annual probability of exceeding particular ground motions for Metro Vancouver. And then for this example, I'm talking about what the shaking would be like for Vancouver at a relatively stiff ground condition or a shear wave velocity of 760 meters per second. So the ground motions could get as high as 0.19 g, 10% the acceleration of gravity, over 10% the acceleration of gravity, at which strong motions or damage might start to occur. This has a 0.2% annual probability of exceedance. It's 0.2% probable that we would exceed that level of shaking in any given year, or that there's a mean average 475-year return period for that level of shaking. If we look at a longer return period or a lower annual probability of exceedance, the ground shaking levels will go up. What I need you to understand is we're going to make maps for these two different return periods and therefore two different intensities of shaking as we feed that into the information. The difference is that the 475-year return period tends to have 2 to 2.5 times lower seismic intensities than the rarer, longer return period of 2475 years. So that's a very good information to have behind the knowledge in our maps. When we compare a 475-year to a 2475-year return period map, we're talking about the seismic intensity of that map has gone up by about 2 to 2.5 times. One last caveat or details about how complicated it is, and it's in the subsurface ground conditions in Metro Vancouver, is that we have beautiful tall mountains on the North Shore, and then we have a low lands extending to the south, and that's sitting within that Georgia Basin. And this is when it was full of sediments back when dinosaurs were roaming the world, but it's turned into sedimentary rocks now. And since then, glaciers have come and deposited debris from the mountains into Vancouver, Burnaby, Surrey, creating uplands or hills. And then in the last 13,000 years, since the last glaciers melted, we have brought a lot of sands, silts, and clays and filled in the Fraser River Delta. The delta itself is about 300 meters thick of these soft sands or silts, and that's a pretty crazy depth in terms of other places in Canada. Usually, these young sediments tend to be about 100 meters thick somewhere else in Canada. So the scale of what we're dealing with is very different in Metro Vancouver. So some background on seismic microzonation mapping. What is it? Well, the first thing to convey to you is that the effect of earthquake shaking is never uniform. It will always feel different here versus over there. In general, the further the distance you are from an earthquake, the lower the shaking intensity or the attenuation will decrease that energy. But the fact that I'm standing on rock and the fact that you're in thick sediments elsewhere, that will change how the earthquake shaking is experienced. So we work towards the process of seismic microzonation is try to depict on a map where these zones are that will be amplified or de-amplified, where shaking will be increased or decreased in comparison to a reference ground condition. We use maps which help us communicate relatively extensive and complex information. And this plays a critical role in making this information accessible to a variety of users, both technical seismic experts, but also what we would call non-technical or intermediate users who need to make predictions, say risk or loss estimates based on what the hazard is. So to produce seismic microzonation maps, we absolutely have to have some information about the subsurface ground conditions from geology, geophysics, as well as the geotechnics, or how that soil will behave under strong strains or through cyclic loading. As well as we'll have to perform some sophisticated seismic hazard analyses and numerical modeling to predict what the ground shaking will be given those subsurface ground conditions. So maybe at this point, you're aware, or it's not a surprise, that not every seismic microzonation map would be the same then. It depends on the amount of data and the quality of that data that you're using. And therefore, the more you use and the better it is, you can push and make a more detailed map or more detailed resolution of the mapping. But as a first pass, you're going to look at what the subsurface ground conditions are like, and that will give you an idea of the susceptibility to that seismic hazard. Could it fail? Or could the shaking be higher? But we would push to level 3 by including what that input shaking intensity would be in combination with what we understand about the subsurface ground conditions to produce an actual hazard map. And I am sure you can appreciate that the more time and effort and data that goes into it, the cost or the expensive nature of the seismic microzonation mapping increases. Another way to say it is you don't start at level 3. You have to start from level 2, build to level 3 over time and with data and with expertise. If you read literature about seismic microzonation mapping, they tell you that this type of output is beneficial or very useful. Technical experts, earthquake engineering professionals should be using these maps to understand risk and inform disaster risk reduction or improve their understanding of the regional variability in the region. These maps are also supposed to be useful to intermediate users, such as insurers or reinsurers or land use planners. They're supposed to be able to use these maps for emergency response planning, land use planning, or for loss calculations for the insurance industry. Of course, these maps are also usually available online publicly, and all kinds of professions might access them for various reasons. But that's theory. I've found out in practice it's not that easy. Even myself, as a technical creator of seismic microzonation maps, I find myself sometimes hard pressed to explain it. And we are aware that we're trying to reach a whole bunch of different people with these maps, and they come from very different backgrounds and expectations. And so there's a real challenge in people even understanding the maps in order to be able to apply them and use them effectively. I want to conclude here with this background on microzonation mapping to give you some key facts about seismic microzonation mapping in Canada. Number one, there's no Canadian standard or guideline for seismic microzonation mapping. We could do whatever we wanted. It's actually quite apparent in the map images at the bottom that there is no standard. All of these maps are displaying seismic site class, but the fact that they all look so different doesn't help us understand what they're trying to portray. Second is that there's no existing seismic microzonation maps in Canada that have been made accessible in digital or GIS layer form. I don't know why. The last maps are being made in 2018. Even then, we could have been making them digitally available. I would say that these two facts are a major hindrance to the comprehension and use of seismic microzonation maps in Canada until now. Last thing I want to hammer home to you is that there's very few level 3 seismic microzonation maps in Canada. All the maps I'm showing you are seismic susceptibility. It's an indication of how seismic shaking might alter, but we haven't fed in what the actual regional seismic hazard intensity is to these maps to understand how they really will amplify or de-amplify the motions. So I would say it this way, that we have very little experience with access and therefore the use of level 3 seismic microzonation maps in Canada. We're making them now. How are we going to use them in future? At this stage, I'd like to give you some key outcomes of the project. Number one is that we're pushing to make these level 3 seismic microzonation maps, which is relatively unique or rare, or very state-of-the-art. We don't have any kind of standard or guideline to follow. We understand that end users will be limited in their comprehension and therefore the use of these maps. And so to combat against that, we've worked with the engineers and geoscientists of BC to form a technical peer review committee so that there's now a handful of practicing geoscientists and engineers in Metro Vancouver who've been able to understand what these maps are and how they've been developed over the last 7 years. They also, EGBC has worked towards development and use of seismic microzonation maps as guidelines or standards. And that's a good push towards having Canadian standards or guidelines. We also know that the end users could be non-technical or intermediate users, and we need to promote comprehension and use through our knowledge sharing of how we've made these maps and what they're depicting. So we've included regular engagement opportunities throughout the project and involved non-technical users in our peer review process. And so that's not normally accomplished in a seismic microzonation mapping project. Last to say is that if you're interested in earthquakes or a geotechnical engineering student in Canada, it's a pretty sweet deal to be able to work on this project. The opportunities and the wide range of the science and engineering that's involved make it a pretty cool project to have been part of. Now comes the show and tell of the 29 maps quickly, and then I'll talk through how we made them for you here on the slide. These maps are just susceptibility. These maps are just an expression of what we now know about the subsurface ground conditions in Metro Vancouver. It's us trying to display to you the geodatabase that we've developed. Then we take that information and we turn it into, feed in that input seismic intensity and feed it through the ground motion, the under subsurface ground conditions for these two return periods or these two seismic intensities. And then we can look at what the liquefaction hazard potential, the landslide hazard potential, and the increase to seismic shaking in reds and oranges, and the decrease or de-amplification of seismic shaking would be in green, as well as how the underlying three-dimensional Georgia Basin may alter earthquake shaking. In this case, how it will increase those seismic shaking at those long periods. So we've made 29 maps. Let me try and walk you through how we made them. So we had to compile a bunch of data for the subsurface in order to understand the subsurface ground conditions and make our predictions. We start with compiling available data that's available online, but then we also solicited or talked to local governments, engineering firms in the region, and asked for access to the data they had collected over the last decades. The project spent time and effort on students to extract that information from paper records, digital files, logs of the testing. We've ended up with 15,000 unique geodata locations. And at each location, we understand what the subsurface ground conditions are like with depth as well. So there's more data than 15,000. In addition, the project also has funded seismic field campaigns for 5 summers and continuing into 2024 and 2025. In this way, we perform multi-method non-invasive seismic testing. This allows us to quickly cover ground, find out what that particular period or frequency of vibration the ground has at over 2,300 locations, and also target what the detailed shear wave velocity or stiffness of the ground is like at over 120 locations. This is very helpful for us to achieve the spatial coverage that we're aiming for and improve that there's a geodata location or some kind of evidence of what the subsurface ground conditions are like at every 200-ish meters or so, or the resolution we're aiming for. Last thing to say is that if we relied on only one type of measurement, we wouldn't be able to know what we know now. It's been key or pivotal to have all these types of data to infer or understand the conditions of the different layers. Another way to say it is some methods hit refusal or they don't go any further, but seismic waves and seismic energy can travel through that. And we can record that with seismometers to understand the properties of that material. Here we go. Here's the quick show and tell of how we've achieved our seismic hazard mapping, which is depicting earthquake shaking in terms of whether it's been de-amplified, the intensities are decreased relative to a reference ground condition, or whether they've been amplified or increased relative to that reference ground condition. And these maps are inclusive of the one-dimensional site effect, or as the waves propagate up through the soil column, but also uniquely, never been done before in anywhere in Canada, including a three-dimensional sedimentary basin effects. So we turn our geodatabase into what we would consider seismic susceptibility maps. These maps depict to us how earthquake ground motions may be altered, knowing where sands or clays or rock are present and how old they are or how stiff they might be. We also now have 2 different maps. I'm showing you one that depicts the depth of the sediments in Metro Vancouver, and that we would know where there's shallower or deeper sediments. We also have mapped where the velocities or the shear modulus, or how easy it is to shear or tear that material in maps as well. So we know where stiffer ground is and we know where softer ground is. If you combine the fact that it could be soft or thick, if you combine how thick it is and how stiff it is, you could understand what the site period might be, or how that ground will filter that seismic shaking, and therefore what the vibration feeling would be like. So where it's stiff and shallow, we would experience shorter period shaking or very rapid shaking in comparison to a site that's softer or thicker. Again, these are all maps that just express the information that we understand about the subsurface ground conditions, but it doesn't answer this question about how much will the ground increase or decrease the earthquake shaking, considering a probability or a rate of occurrence. We've chosen 2 different rates of occurrence or mean return periods. So we need to select and scale those input time motions for those annual probabilities of exceedance. We feed that through the soil column and 55 models across the Vancouver region. And we perform that for 3 different types of analyses, ending up with 11,000 answers as to what the seismic shaking is like at these 55 sites. We understand what the properties are like at those sites. We understand that we can correlate that type of response elsewhere and map it out regionally and group what the response would be like for particular zones and end up with a microzonation of the seismic shaking. Now, let's not forget the fact that we're inside of a sedimentary basin and that we would experience potentially increased shaking intensities at very long periods related to the very long wavelengths of several tens of kilometers by 6 kilometer wide or deep sedimentary basin. So we run simulations that include earthquake rupture for 8 crustal scenarios, 6 in-slab scenarios, and end up with over 300,000 synthetic ground motions to understand or anticipate what that earthquake shaking will be like in Metro Vancouver. You can see that the simulation that we're watching was for an in-slab earthquake. So it took 10 seconds for that seismic energy even to reach the surface. And then it propagated towards Metro Vancouver, which is over here. And it traversed over the Georgia Basin in the middle. And you can see that the seismic energy is amplified. The reds and blues get higher and they last longer. Surface waves are generated and slosh back and forth or get trapped inside of this basin and lead to that increased seismic motion. So once we do all that, we also don't want to double count the shaking intensity of the site and the basin. So we do some tricks to not double count that amplification so that we have a pure basin amplification to multiply with our site amplification. We create basin amplification maps to convey the answer that we have in terms of how the Georgia Basin will be amplifying ground motions in Metro Vancouver. We combine that with the seismic shaking we anticipate from the soil column, and we end up with the seismic hazard shaking maps that combines these 2 effects for these long periods at 2 and 5 seconds. Ultimately, we create 12 shaking hazard maps for 2 different return periods and 5 spectral periods. How you use these maps is you can see that in the north part of Metro Vancouver, it's green to yellow to orange. Sorry, it's yellow and orange at short periods or for a peak ground acceleration. Very short period shaking. Whereas at longer periods, you see reds and orange increased ground shaking at longer periods in the Fraser River Delta, where the sediments are much softer, thicker, and over the Georgia Basin. Basically, the maps are depicting that the ground shaking intensity will be very different across Metro Vancouver because of the subsurface ground conditions. And you can anticipate that the shaking will be increased at different periods based on how thick or soft that material is. For liquefaction hazard mapping, we start with identifying where the natural ground is susceptible to liquefaction. This is very easy. You find a geology map. You figure out if it's sandy. You figure out if it's saturated. And you get this qualitative guess as to whether it's susceptible to liquefaction. If we're talking about predicting the weather, this is the equivalent of looking out the window. But we did spend 7 years creating a geodatabase. So we can check how resistive the ground is to being induced into liquefying. And so we use that information to confirm or update our liquefaction susceptibility rating based only on geology. So it looks like we colored the geology map with just based on what we assumed liquefaction might be. but we have checked how resistive the ground is at many locations to ensure that the susceptibility rating is justified or governed by data. So we would consider this a level 2 liquefaction susceptibility map. But that's only susceptibility. The question we want to answer is, will the natural ground liquefy given the regional seismic hazard? Or given what we know about earthquakes happening, how frequently and where, we want to know whether that ground will liquefy. It's susceptible to liquefaction, but will it liquefy? In order to do that, we calculate how likely or will liquefaction be occurring in the top 20 meters based on a profile or measurements of the soil resistance. And we compare the soil resistance to what the input seismic shaking demand will be. This gives us a ratio to let us know about the factor of safety of liquefaction. We want to know what's that mean annual rate. We need to understand what that return period or rate of that ground motion intensity will be from our 6th generation Canadian seismic hazard model or the 2020 National Building Code seismic design motions. We understand what the soil resistance is, and then we can anticipate the mean probability or the annual probability at which LPI will be exceeded. So the map depicts or shows is based on these quantitative LPI values, and that hazard rating is assigned based on the correlation of LPI with other worldwide observed seismic-induced liquefaction effects. We accomplished that and achieved this mapping having calculated a hazard LPI curve for over 1,000 locations in Metro Vancouver. For our landslide hazard mapping, we follow similar procedure where we start with a good guess based on geology, ground conditions, what the material type is, and how saturated it might be. In general, if it's a steep slope, it's likely to fail. If the material is very weak, it's likely to fail. These are good choices at a first pass. But again, we have a geodatabase that tells us a little bit more information or a little more measurement about that subsurface ground condition. And we build over 200 two-dimensional models to sample over what the slope heights and angles are in the Metro Vancouver region to understand how likely the slopes are to fail. So a slope with a very low critical acceleration and a very high landslide susceptibility means I don't have to give it too much of a shove before it's going to start to fail. But then the question is, will they fail, given what we know about earthquake occurrences in Metro Vancouver? And to do that, we need to understand the mean probability or the annual rate at which landslide sliding displacements will be triggered. So again, we need to know how frequently the ground motions will be exceeded or what that probability of exceedance is for this return period that we're considering. We need to know what that critical acceleration of the slope or how resistive the slope is to being pushed and starting to fail in order to anticipate what the sliding displacement is for the slope, and therefore converting that to a hazard rating based on the correlation of these predicted sliding displacements with other worldwide observed landslide effects. So that was quite the tour. And in theory, you should understand how these maps have been made and how you can use them. But I know and appreciate it's even difficult for me to have tried to summarize that for you. And so we've worked on trying to talk to people and end users over time. And about 2 years into our project, we finally started to have draft versions of the maps to talk about. And we also tried to have a nationwide survey online about who uses Canadian seismic microzonation maps. Do they understand them? And how are they using them? It's not a surprise that people who make seismic microzonation maps like myself, as well as what we would call technical end users or those in the earthquake engineering profession or seismic experts, are not only familiar or aware of these maps, but over 80% of this type of profession is using the maps. What's interesting is that non-technical end users maybe insurers like yourself say they're very aware of these Canadian seismic microzonation maps that exist for other cities in Canada. Over 60% of non-technical end users say that, but it decreases by half in terms of who uses them. Non-technical end users, only about 30% are actually using these region-specific or kind of detailed seismic hazard maps. We also ran a workshop in 2019 to start to gather how we show the map and what kind of metrics or what we're mapping. Is that helpful? Can people understand that? And with 36 participants, we reinforce the usual outcomes that I talked about before, that it's challenging for a non-technical audience to readily understand these technical aspects of the seismic hazard and related metrics. So it continues to reinforce this need for standardization of seismic microzonation mapping. And there is a very strong request for digital data and maps. So we are going to make the maps digitally available. I'm not convinced that just because you'll be able to now work with the map directly, that's going to solve all our problems. I think it's still complicated and still a issue understanding what these maps are trying to depict. What we've done also since 2022 and into 2024 was meet with practicing geoscientists and engineers in British Columbia to explain these maps and have them review the processes, methodologies that we use to make them. And EGBC also worked towards creating professional practice guidelines. Into 2023, we started to let the Canadian earthquake engineering community know how we made these maps and that they're going to be available. In the fall of 2023, we last held an engagement exercise on feedback about our liquefaction mapping. And now here I am in 2024, working on providing education and training sessions to planners, insurers like yourself, as well as the local governments and First Nation communities in Metro Vancouver. We hope that that's helping solve some of the issues of comprehension and use of the maps. Specifically, you'll be able to access these professional practice guidelines sometime this month, maybe next month, on the development and use of seismic microzonation maps. These guidelines, so there's a place that you can go to look on what a common approach to development of seismic microzonation maps should be in Metro Vancouver or British Columbia. So if you're a community and want to create your own seismic microzonation map in future, you can see what kind of data and what kind of timeline and what kind of expertise is required to get to a level 2 or a level 3 seismic microzonation map in terms of liquefaction, landslide, or shaking for your community. The guidelines also discuss the use of seismic microzonation maps or try to convey what the professional practice should be in using these maps. So for example, for structural and geotechnical engineers, they should be using these maps to gauge the variability in the regional seismic hazards. And that regional scale maps are perfect for regional scale scoping to risk studies. If you have linear infrastructure that like bridges, roadways, railways that extend past local municipal governments or site scale, these maps are more ideal for these larger scale type projects. Applications that are assumed local governments, First Nations, or the treaty nations will be able to use these maps is that for hazard and urban planning and permitting, asset management, and emergency response. I'm aware I might be talking to an insurance industry audience, and so I've got some thoughts to share with you on how you might apply or use our maps. First and foremost, these maps are just hazard. They're not risk or loss. So they're going to serve as inputs or definitely updates to existing seismic risk and loss estimates currently. Basically, the access is going to have to come from the industry's integration of our project map results and data into new CAT models. You should be asking for these region-specific updates to be included in CAT models used by your company in the coming decade. I should reinforce that earthquake shaking is just going to occur everywhere in Metro Vancouver. And so potentially the industry should just be pushing towards a general uptake of earthquake insurance for all of Metro Vancouver. For me, I'd like to try to explain how I think it's useful to have these hazard maps for two different return periods. We could have made it easier on ourselves or just make maps for one return period, but that's not actually super useful. In order to build new buildings or bridges in Canada, you would base your seismic design on a very long return period, or the 475 years. Whereas if you're working on financial risk assessments, my knowledge is that you would look at maybe a 475 or 500-year return period. So that's why we created these maps at these two different return periods. For me, I find it very beneficial to compare the maps for the two different return periods. And if I see a community or a zone that already has a moderate, high, or very high hazard rating for the shorter 475-year return period, essentially considering a lower shaking intensity or a higher annual probability of exceedance, I should prioritize stuff, planning, mitigation, adaptation, insurance in these locations. In terms of brokers, maybe how you might change insurance policies, it is possible probably to prioritize or develop specialized policies for areas where earthquake shaking is expected to be increased. So for example, in northern part of Metro Vancouver, you're going to experience increased shaking at shorter periods. And that ultimately usually leads to damage to shorter or smaller structures or acceleration sensitive non-structural components. So I have no idea if you can create insurance policies that are this specialized, but maybe that's the point, is that these maps are now permit that or give that level of information. Last, in terms of how you would use maybe the liquefaction landslide hazard potential maps, is that it's conveying that landslides and liquefaction don't happen everywhere. And so you could target additional earthquake insurance coverage or additional living expenses coverage in these identified areas. In terms of the risk profiling, I just have to continue to reinforce the fact that these maps or this region-specific knowledge is new and not currently part of any existing seismic risk assessments. Our maps are based on better information. We model or predict seismic shaking based on several parameters, and that's more sophisticated and more detailed than the National Seismic Hazard Model, which only uses one parameter, VS30 currently. And we have more detailed site information. So our region scale hazard mapping needs to be included in seismic risk analyses to basically understand the predicted impact to structural damage and thereby loss estimation. Another thing I should emphasize is that our mapping includes regional shaking due to the basin effect, or that three-dimensional Georgia basin. That is a scale that does not work at the national scale, and it doesn't work at a site-specific scale unless it's very critical infrastructure. It's actually so state-of-the-art that very few seismic designs are including wave propagation simulations. It would be very specialized to include that currently. So the only place or the only way we've made this information available is this project and in these maps until now. Last to say or reinforce is that those liquefaction and landslide hazards are concentrated in particular areas or zones, and they don't occur everywhere. So to conclude, how are you going to get your hands on these maps or these data sets in future? We're publishing the maps as PDF files, and in this way we are very clear about how we want that map to look and how we want to convey that information. And I think you appreciate that that has evolved over time in conversation with anticipation of how people could use these maps. And so we'll have an explanation on the right-hand side. We're going to try for very clear legend or explanation. But this is the place you would go to see how we think the map should be conveyed and used. But we also have a project website where you can check our publications or presentations And inside of that, we're developing an open data portal where you can have access to these published maps and also be able to interact with the maps in an ArcGIS environment online. Zoom in, zoom out, put one on top of the other, decide whether or not you want to download those maps. Once you download the GIS file, you'll have access to the map values and potentially other columns of information, but you won't have the very detailed information at every discrete depth of every measurement. And that may be available in the coming months. So thank you for your time. A reminder that we're aiming to release these region-specific seismic hazard maps for Western Metro Vancouver this summer. We'll continue doing seismic microzonation map into the eastern communities of Metro Vancouver, and finally producing those final maps in late 2026. Thank you for the time, and I'm open to answering the questions.
Fabulous presentation. Thank you so much, Sherry. I've been looking forward to this end of this project since shortly after you began it. So it's really exciting to see it come to fruition. We have several questions. I have several of my own, but I'm going to offer those of our attendees first. Charmaine Flugrath asks, the risk knowledge provided from the strong motion maps that were provided to government entities and geosector professionals, Charmaine is talking about EGBC, will result in risk transfer and force risk tolerance to governments, especially local governments, as well as demand risk acceptance by local governments. Should these maps be relied on to risk inform and risk transfer to developers and property owners? Wow, this is a very packed question. And also be used by the insurance sector to gauge eligibility for insurance or influence insurance premium. So a lot there. Maybe I'll unpack that a little bit. I think that you've talked about some of the uses that you think insurers should put the maps to. In particular, do you think that insurers should use them to gauge eligibility for insurance, or should they be used to influence premiums?
The short answer is yes. I mean, the maps are depicting where seismic shaking will be increased or decreased on average for these different intensities or different return periods. And so it is possible to get into the weeds or details in terms of a premium for earthquake insurance. And so maybe earthquake insurance doesn't cost the same all across Metro Vancouver. I don't know how sophisticated or what level we're at in insurance policies. I think that just the fact that increasing people having earthquake insurance in Metro Vancouver is the low bar that I would set for these maps.
Armin, I see that you've got your hand raised. Please chat your question into the Q&A box. Okay, so actually, I want to follow up on Charmaine's question about premiums. You have provided ground shaking maps for 475 and 2475 return periods, but premiums are ideally driven by average annualized loss, or at least in many circumstances, they're driven by average annualized loss. So you spread out the loss on a long-term average basis, and then you add a risk load to it. So, you might pay insurance that costs 50% more than the insurer expects to pay you on a long-term average, 50, 60, 75%, something like that. And those average annualized losses, they tend to be strongly sensitive to lower return periods. They tend to be far more sensitive to the 74-year shaking than to the 500-year shaking and the 2475 shaking. you contrasted, you talked about your choice between publishing one map and two, and you landed on two. Did you think about publishing three and choose not to publish three, or think about publishing four, but still landed on two?
We did not, I think the short answer is we went as far as two. I don't think we ever were thinking we should make more than that. In that there's only so many maps that we can make, and we chose two return periods that we thought would be the most useful, or are used most commonly. Yeah.
Makes sense. Let's see. You answered the second question, which was, are they going to be available? Louis-Philippe Caron asks, Delta and Richmond have long been known as potential liquefaction zones. What makes your study unique?
That's right, yes. So a liquefaction susceptibility map was always going to look dark colored for the Fraser River Delta. It's young, sandy, saturated. It is highly susceptible to liquefaction. What's interesting though is that I didn't know how hazardous it could be given earthquake shaking. And the map there, if you contrast it with the landslides, even for the shorter return period, we see relatively high to very high liquefaction hazard for the Fraser River Delta, but we don't see the same kind of area coverage of high to very high landslide hazard. So that at this more frequent level of shaking, we still anticipate that the liquefaction to be occurring in the Fraser River Delta, but that there won't be as many landslides triggered in terms of the area covered. So that our study is not new in describing the long known susceptibility, but also hazard of liquefaction in the Fraser River Delta. And another way to say it is geotechnical engineers have known for a long time. Our project simply repeats what kind of a site-specific geotechnical engineer would do at each of the 1,000 locations we had the data, and then we try to map that out regionally. So it's not like geotechnical engineers hadn't known this. And so there has been densification of the ground. There has been ways to try to mitigate against this. And so the maps are scarier than reality because there has been engineering accomplished to try to combat against this. And conversely, for shaking hazard, you have buildings that were built before the 1980s and before we understood what kind of hazard there was from the Cascadia subduction zone. So there is infrastructure that wasn't built to withstand the now known seismicity or seismic occurrences that we know now. But I would say it feels like most of what we've been building on the Fraser River Delta has known about the subsurface ground conditions and the likelihood of liquefaction. And so our maps are not verbatim as to what the ground is like in Metro Vancouver. It's like what the ground was like before we started building.
And I mean, I'd add that yes, we've known about the problem of liquefaction for a long time, but knowing a problem exists and having these detailed maps is two different things. The detailed maps tell us much more than just there is a problem, right?
Yeah, yeah.
Awesome. Mehdi Hosseini asks, do you have a map showing depth of firm ground and bedrock in the lower mainland? That's your Z1 and Z2.5 maps, right? Could you explain?
Basically, maybe we have 4 maps that try to convey depths of stuff. So we have a depth of post-glacial sediments that we call HPG, or the thickness of post-glacial sediments. That's the depth to get to glaciated or stiff ground, or Pleistocene age glacial sediments. That's one map. We have another map that's the total soil thickness. So all of the soft sediments as well as the glaciated sediments. So depth to rock, that's our second map. Then we also have these two other maps that try to convey the depths or velocities of the Georgia Basin. That's a Z 1.5 and Z 2.2 maps. Z being the depth at which 1.5 kilometers per second velocity occurs in the subsurface. So all four of those maps are very helpful in giving you an idea of the depth of each kind of horizon, or very important seismic impedance contrast in the subsurface.
Awesome. Charmaine Flugrath asks, would it be possible to have somebody on your team provide a presentation by request to local government? And Charmaine lists a bunch of different people within local government who'd be interested in hearing your presentation.
I should be better prepared, but we are offering or running a session on May 22nd in Metro Vancouver for local governments and First Nations. So EMCR has been in contact with the local governments and First Nations to invite representatives to attend that session.
So if Charmaine wanted to look for that session, should where do you get more information about that?
Yep, she could actually, since my email's up on the screen, she could send me an email and I'll link her, make sure that the invitation arrives for her. Yep.
Awesome, thanks. Our anonymous attendee asks, how should the basin maps be used in conjunction with the National Building Code of Canada? Is amplification in large area, does amplification in large areas of Lower Mainland increase? Or basically, how are your maps going to change what we know compared with the National Building Code of Canada?
It's an easy but tough question. Easy in that there are now maps, which were never available before, trying to show where we anticipate the shaking from the Georgia Basin to be greater than what we would anticipate from VS30 alone, or just knowing what the subsurface ground conditions are like. The map is a bit weird, and there in the very southwest corner, it's kind of red because you're over the deep Georgia Basin. And then there's like this gap, and that gap exists because what we predict from the soils is enough. We don't need to add any more due to the basin. But then we also see kind of the need to add back amplitude of shaking at these long periods in southern Vancouver, southwest Surrey, and into White Rock, because they're still in the basin, but they're stiff enough that nobody would have anticipated this long period shaking in the National Building Code or driven from ground motion prediction equations. There's not enough information. No. The National Building Code, based on VS30 alone, would not have predicted that the amplitude of shaking would be that high in southern Vancouver, southwest Surrey, or White Rock, because the ground conditions are stiff enough that they wouldn't have expected that. But lo and behold, this type of ground is inside of a sedimentary basin. And we do anticipate that there will be increased shaking intensities at these long periods, even though it's a bit unusual that the stiff site is inside of a basin.
That's really interesting. I mean, one of my questions was, I was going to ask you about comparison with global VS30 maps, just so that we're not talking over people's heads. VS30 is a parameter, an attribute of the soil that's within 30 meters of the surface of the ground surface, that earthquake engineers use to estimate how strongly the ground will shake. And we have a global map of it, but we don't have a global map of the basin effects that you're talking about. And both those things, as you've just said, affect how strongly the base of a building will shake. And you've just said that second part really matters, that it strongly affects the shaking, at least in certain regions. Can you tell us how much, how big a difference the the consideration of the basin effects makes in the, like, what you would use for design motions?
Right. The color scale on our basin amplification maps maxes out at about 1.8. So we anticipate up to almost 2 times the average increase in the amplification or the shaking. But that's on average. It can be much higher than that. And it's also very scenario dependent. We also average it out for all the scenarios. So maybe the audience is savvy enough to understand we're looking at an average, but there's a huge standard deviation or uncertainty around that. And for any given earthquake, it could be way much higher or a lot lower. But we are depicting the average basin amplification at 2 seconds and longer. We know that information at 2, 3, 4, 5 seconds, but we only display it on a map at 2 and 5 seconds. And those now it's coming to me that those amplifications are strongest around 2 to 3 seconds. They're even less at 5 seconds. So if you compare the 2-second basin amplification map, those values are higher than the 5 seconds. So we anticipate, another way to say it is our basin amplifies shaking closer to 2 to 3 seconds than it does at 4 to 5 seconds.
And
So
this affects 20-story buildings, right?
that's right. 2 seconds would be a rough back of the envelope, would be roughly a 20-story building. That's right. Yeah.
So these motions, we're not talking about the strip mall that's a single story.
No.
Okay. So the basin effects, that's what where we really need to worry about basin effects is places like the ones you're talking about, and it affects buildings like the ones that collapsed in Mexico City in 1985 for basically the same reasons. Is that right? Sort of the same reasons?
Yes. The same reasons. Yeah, and I guess it was amplified at 2 seconds in Mexico City. So around those 10 to 20-story buildings. Yeah.
So the maps that you're making are going to help us avoid the kind of collapses and disaster that happened in 1985 in Mexico City, among other things.
It would be nice to think so, yes. I mean, some things have already been built, right? But now you know, and now you know whether to advocate for change in some way. Yeah.
Awesome. Let's see. Mehdi thanks us both. You're quite welcome. Let's go back. We've got a lot of time left, so I've got some questions of my own. So one of them is $4 million. Can sound like a lot of money, and 9 years of work can sound like a lot of time and effort. Not mega science, but bordering on it when it comes to earthquake engineering. Can you put that in context? Why you think it makes sense for society to spend that kind of money? For example, how can you quantify how it's going to help us save money or lives in the future?
There is a number that I should know off the top of my head that, $1 of prevention is $100 to recovery. There's something like an order of magnitude. It might be 10 to 100 factor that if you put $1 into the mitigation or adaptation or this preservation or trying to prepare ahead of time, it saves the money in the end in terms of response and recovery. So the project was awarded in 2017, and we received at that time around $3 million. And it felt like a lot for our project, but we were a little piece of $80 million that was being provided by the province at that time towards disaster risk mitigation projects and studies. So I want to reinforce that the province of BC is very aware that they live in a geologic and wonderful climate environment, beautiful to live in, but also geohazardly high in comparison to my backyard in London, Ontario. And so these investments are needed, and they are doing it. But then, yeah, I also led a hazards risk resilience field school in 2022 when we came to BC, because they had a pretty bad fall in 2021. It is rough having to recover from these hazards. In seismic, the scale of what can happen is so much more than what we've had to endure already. And so it's, as someone who works in seismic hazards, it's tough to try to pile on how hard it is to deal with it already. But we absolutely have no idea how bad it could be. I think, like, think of Turkey, you know, it's not that our design codes or compliance with design codes are poor here in Canada. It's just that there's going to be surprises. We try to anticipate, but it's going to happen. And we haven't had to deal with it in our lifetimes, or in a couple of lifetimes, like other countries have to do. Chile, Japan, their building stock and their people go through tests of how their seismic design, how good their seismic design is. We don't go through these tests. So we'll be tested probably once really rough.
Right, right. So Charmaine tells us that the mitigation response and recovery formula is $1 spent in mitigation and prevention saves $7 in future response costs and a further $13 in future recovery costs. So she's saying 20 to 1 is their benefit cost ratio. Now that's, I think she's talking about you know, you put $1 in of greater strength into a building, and you avoid $20 in future losses. And I think it's important to distinguish between that, you know, that capital cost and the knowledge cost. I strongly suspect that the benefit cost ratio for the kind of knowledge that you're producing is much higher than this 20 to 1 or other benefit cost ratios that talk about added capital cost, because you can't justify the added design, the added cost for design without this kind of knowledge.
That's right. Yeah.
It almost doesn't, you know, the research that you're doing here seems more fundamental to mitigation than, you know, than the kinds of benefit cost ratios that, you know, that you get out of actual mitigation, because the study that you're doing makes it clearer that we've got a problem that needs addressing, right? You are eliminating some of the uncertainty that can, you know, prevent any kind of decision making in the first place. It's the kind of information that you're producing that makes us decide to do something in the first place.
Right.
And only after you decided to do it do you think about the costs and the benefits of what it costs to actually do it.
Right. Yeah, there's two things. One was with the technical peer review committee. I assumed these maps would be instantly useful for engineers, but they're constrained to codes, rules, and fair enough. But so our maps cannot replace code design values. So our maps are not readily used in this way. However, our maps identify how it is different from the current code. And it is a piece of evidence to have that conversation with your client as to why you may need bigger columns, or why the ground needs to be safer against liquefaction. That's where engineers could use it. But another thing I think that I forget to champion more about the project is I have no idea how any local government or First Nation community could have achieved this on their own. The province has invested to make sure that this is available for all of the local communities and all of the local governments. Now, it is a challenge now how to deal with it, but it wouldn't have existed without the decision to have made it in the first place. And I have, just like I was talking today, I don't know how insurance policies, how much detail could get into them. I don't know what every local government is going to have to do or could do with these maps, but this is the most detailed information about how earthquake shaking will vary in the Metro Vancouver region, where earthquakes or landslides could be triggered, at what shaking intensity will they be triggered. Never really shown regionally before, never actually justified or proven or quantitatively assessed fully to the same level.
Yeah, this is clearly a first for Canada. Naveed Sarus asks, can you explain more about ground motion simulation used in Vancouver? What methods did you use for the study? I'm thinking of that beautiful video that you have of wave propagation, and I think that may be what Naveed is thinking about as well.
Right. So it's relatively complicated and sophisticated. I didn't have time to talk about it in great detail, but if you're a geotechnical engineer, you want to predict seismic shaking for a high consequence, or the code gives you the values. You don't even have to do anything very detailed, but maybe the client wants you to predict the ground motions at the surface for that site, given the ground conditions. So you would build your own model of what the soil is like and propagate the motions through that soil column. It's very standard, or every geotechnical engineer who does seismic design knows how to do this. The three-dimensional Georgia Basin is a model that is millions of grid cells, or it's a mesh. Every 250 meters, we have a value of what it's like in the subsurface, up to 60 kilometers depth. That's a big file. We then have to feed in a rupture model, get that started inside of the volume model, and use three-dimensional wave equations to propagate the stresses and displacements between the cells to predict what the surface ground shaking would be. And so our model for all of Southwest BC is hundreds of kilometers, 180, 100, 200 kilometers wide, by the same laterally, 60 kilometers depth. And we save the ground motions every 500 meters. So this is a big file. This is a lot of answers. It can only be done with high performance computing, very specialized. Your typical engineering firm is not doing this. It is not part of site specific. Our project is doing it for regional scale seismic hazard. You wouldn't do it to predict or try to design for a building at a location.
Our anonymous attendee asks, how is the work on liquefaction risk and basin effects going to inform the next generation of the national building code? Or maybe I'll broaden that. How do you see your products, your deliverables feeding into future building codes?
I think that we haven't yet, but we're pushing towards potentially replacing the existing kind of amplification models that are in ground motion predictions and replacing it with a region specific one. Right now, the National Building Code uses 4 ground motion prediction equations for each source type for the source zones across Canada. And in those models are built from earthquake data sets from around the world. And they anticipate what the ground conditions will do based on the summarized knowledge about that ground condition for that recorded earthquake motion at that station. And it's all very averaged out or smoothed out in a way. And so our project enables us to understand that average or smooth answer isn't totally appropriate potentially for the site conditions in Metro Vancouver or other locations in Canada. So the mean or median ground motion that's being predicted by the National Seismic model is going to maybe end up being the same roughly mean or median, but we can tighten what the uncertainty is around that based on improvement in understanding how the ground can alter that earthquake shaking.
Cool. You have a long list of deliverables and stuff that you're going to post and so on. I would ask, I get a lot of value out of videos like the one that you showed. They make the whole thing seem more tangible. So
Right.
to the extent that you can, I would beg you to put up a whole bunch of those videos, even if you don't see their immediate use, or just for communication purposes. They're fabulous.
Mm-hmm.
In shakeout and in the haywired scenario, we use those all the time, and they had great emotional impact. So you spoke. I asked you a moment ago about how to get this stuff into the National Building Code. Another obvious consumer, in addition to engineering, design engineers, is the CAN-SRM seismic risk model, Canada's first seismic risk model. Have you been talking with the developers of CAN-SRM at all about feeding your knowledge to them?
Right. To generate the first one, they use that global VS30 that's available. But they're working now to accumulate and include these seismic microzonation maps that are available for other cities in Canada. We have a meeting set up that they're meeting with me and as well as the other creators of seismic microzonation maps, so that the details of the VS30 can be included in that global VS30 layer that they use in the seismic risk.
Awesome.
So yeah, these maps are infiltrating into national risk faster than they are into the national seismic hazard predictions or models. But then it again is still only based on this one parameter, VS30. And for us to model seismic shaking appropriately in Metro Vancouver, we need to know site period, we need to know VS30, and we need to know the thickness of the post-glacial sediments. We use 3 parameters. Then we also add on at long periods that the shaking will be intensified in particular regions because it's sitting within the Georgia Basin.
You told us that you had entered this project and realized that there were challenged by the fact that there were no professional practice guidelines for creating maps like this. And can you explain why guidelines matter? What your creation of these guidelines are going to do for the kinds of science that you're doing here?
So strangely, presentation is part of comprehension. So if I'm presented with a map that has 9 hazard ratings compared to the same information for the same region scaled down to only 3 hazard ratings, is it helpful to know that to have that hazard discretized further? Or is it just more useful that I just need to know, is it high, low, or moderate? Like, and so it's these types of conversations and decisions that in some cities in Canada, the ground conditions don't vary enough that they shouldn't have 9 scales, but they want to make enough color on the map that they'll use 9 scales. But if we decide that there's a standardization to the variability in the ground conditions that needs to be conveyed, well, that map has 9 colors. Wow, that's a lot of variation. And this map only has 2 colors. That means there's not as much variation. I can understand that immediately. So it's these types of things that there's a hindrance to comprehending the map, because every time you look at one or compare it to another, they change in so many ways. So it takes a minute to stop and look at the legend and come to an understanding of what it's trying to convey.
Absolutely.
I was reluctant, or it took some time to understand, how important this was. I mean, I like making maps. I like coloring the maps. I think this is fun. I like picking the colors. And I don't want to be constrained by guidelines and standards necessarily. But I do understand that if we're going to make these maps again and again over time, and we expect people to use them, they need to be the same, the science or the knowledge that went into the maps should carry through. Last but not least, to harp on about is there are seismic microzonation up till now, up till the 2015 building code, we only needed to know seismic site class, which is based on VS30, but we didn't need to make VS30 maps. So a lot of the existing maps aren't as detailed as we need them to be moving forward. The 2020 building code now says you need to know VS30 for your site, and you can determine seismic design based on that quantitative number, not how it fits into a category. So the detail of our existing seismic microzonation mapping also needs to be updated to stay up to speed with how seismic hazard analysis changes over time.
And just for everyone else's edification, the site classes that you're talking about are ranges of VS30. So there was a site class that goes from 180 meters per second to 360 meters per second. And so it's a kind of a low, medium, high scale. And what you're saying is, okay, we can actually do better than that. And the National Building Code asks you to do better than that, rather than saying low, medium, or high kind of VS30. Tell us what you got to use the VS30 in this equation over here.
Right, the exact number, yeah.
Let's see, there's a couple of questions left, but we are running out of time. So I'm going to have to leave those unanswered. I wonder, do you have any last, final thoughts that you really want us to leave with? Any sort of big picture message for us?
The big picture message is that we are somewhere between site-specific seismic design and the National Building Code. And these maps are a resource to understand shaking variability, shaking hazard in Metro Vancouver better than any of those 2 sources, as in terms of for the region as a whole. That's the best I can do in terms of trying to, the map isn't accurate for your house. It's not, we don't understand every little, how it changes every 10 steps, but we have a better depiction or understanding of how the subsurface is changing on a much more detailed scale than the national mapping or national codes. It's going to take some time for this increased knowledge to make its way into the national and or seismic risk assessments.
But it's a big step forward.
That's right.
Okay, so thank you so much, Sherry. I want to remind our audience that you'll be able to get Sherry's deck in PDF format and share a video of this webinar by around Monday or so. So look at www.iclr.org/workshops on Monday or so for those two resources. And remember that next month on June 14th, we're going to turn back to construction practices when Patrick Foisey of Hague Engineering is going to talk about good and bad roofing and siding. Thank you all so much for attending, and thank you again, Sherry, for speaking to us today.
Thank you so much.
Bye-bye, everybody.